Okay, let's see if we can get through this problem. When I was setting this thing up, I'm trying to figure out how many energy equations I'm going to use, and so I'm looking for places where I have interest in finding energy. So the first thing I think about is that I have this room over here that has no energy in it because the air over here isn't moving significantly. It's at zero elevation. I'll call it zero elevation, and it has atmospheric pressure. So the energy over here is equal to zero. I know that energy. I'm going to call that point zero in the thing. Now, the air comes into the duct, and when it comes into the duct, it begins to move. So it begins to have some kinetic energy. When it has kinetic energy, it had to get it from somewhere. It can't get it from the gravity. So what happens here is that at this point, the pressure goes down. So it gets kinetic energy by robbing the pressure. And so the pressure here actually goes down. So there'll be a little bit of a vacuum. It'll be below atmospheric here. And so the energy has changed. Well, I mean, it's the same amount of energy, but it's a different form. So I'm going to call that point 1. Then they're interested in the pressure across the fan. So what I'm going to do is I'm going to say that I'm going to write a energy equation right here. The pressure here is different because it adds energy because of the fan blades. You'll see that it has the same kinetic energy. So what's going to happen here is the pressure is actually going to go up because of the fan. I'm going to call that point 2. And then the point 3 is going to be right here at the edge, at the exit. In class, I was doing it out here, which I shouldn't do because there's energy that's lost as it comes out of this duct because it expands, quickly expands. So I shouldn't have done that. I should set point 3 to be right here, right at the exit, because here the pressure is atmospheric again. It still has a velocity, but no gravity. All right, so that's point 3. So in class I was doing it out here. I shouldn't do that because there's energy that's lost as it comes flying out of this, duct. So I'm going to take that to be the point 3. Okay. Now, when I write my energy equation, I'm going to use this form right here where I'm dividing by the volume. So I'm going to use the pressure units. So when I'm dealing with the fan, it's going to be the work of the fan over the flow rate. Anyway, so that's the form that I'm going to use. Okay. So back over here, I'm going to apply energy. So I'm going to start with energy from 0 to 0.1. So at that point, the fan's not doing anything, so that's equal to 0. The final energy is the energy at 1, so that's going to be kinetic 1/2 rho times velocity 1 squared plus no gravity plus pressure 1 minus 0 because there's no energy at point 0. Okay, so now in the problem it says that they want it moving no faster than 8 meters per second. So I'm going to try and make that 8 meters per second. So this guy right here is going to be 8. Okay, so there's only one unknown in this, so I can calculate the P1. So I'll do that. P1 is then equal to a negative 1/2 density times 8 squared. Okay, so if you keep your units in kilograms, meters, seconds, and newtons, if you put all your units in that, then you don't have to worry about converting units. They'll come out in the natural way that they should. Okay, so what I'm going to do is I'm just going to calculate that. So let's see, 64 times the density is 1.25 divided by 2. So this is a negative 40. And the unit will be pascals, because that's newtons per square meter. So it's the standard unit. Okay. The next thing is to apply the energy someplace else. So this time I'm going to do between 0 and 0.2. Now, between 0 and I didn't do that in class. In class I did from 1 to 2, but it's all the same. So between 0 and 2, then I do come across the fan, and so the energy that's put into the air is the wattage of the fan times the efficiency of the fan. Okay, and if you remember the formula for the energy is the wattage divided by the volume flow rate. Okay, so wattage divided by the volume flow rate, so we'll call it Q. All right, so that, and it's positive because energy goes in, and that equals the energy at point 2, which is kinetic, 1/2 density times velocity 2 squared, no gravity, and the pressure is P2, minus the energy at point 0, which is 0. Okay, now it's probably pretty obvious that the velocities are the same, but if you aren't sure, then what you can do is you can write the continuity or the conservation of mass. There's no mass going in or out, so the mass at 2 is equal to the mass at 1. The mass at 2 is density times area 2 times velocity 2. The mass at 1 is density times area 1 times velocity 1. The densities are the same. The areas are the same, so the velocities are the same. V2 equals V1. So this guy right here is 8. Now this guy has 2 unknowns. It has the W, the wattage. It also has P2. And I guess if you count it, you also have this one. But I can find the volume flow rate because they tell me that the volume of the room, and they want it to evacuate that in 10 minutes. So what I can do is I can calculate the volume flow rate. So the volume is the total volume per time. So the volume is 2 times 3 times 3, right? 2 times 3 times 3 cubic meters. So that would be 18 cubic meters over 10 minutes. Now you want to put everything in the common units, kilograms, meters, seconds, and newtons. So I got to get rid of the minute. So there will be 1 minute in 60 seconds. All right, so this is going to be cubic meters per second. And so you get my calculator, so that'd be 18 divided by 10 divided by 60. So the Q is equal to 0.03, and it's going to be cubic meters per second. Okay, so I have the Q. So I still have 2 unknowns, and so then I want to apply the energy equation again. And so this time what I'm going to do is apply it between, okay, so I want to apply the energy equation. This time I'm going to go between 2 and 3. I think that might be the easiest thing to do. You could go from 0 all the way through if you want to, but then I have another fan term. Okay, so from 2 to 3, I'm not adding anything. So there's nothing new going in. I'm going to pause this and plug in. Okay. All right, so let's see. I'm doing energy between 2 and 3. So the energy at 3 is equal to the kinetic. It hasn't left the exhaust duct yet. So that would be 1/2. In class, I had taken it outside in the room where it wasn't moving. Okay, but anyway, 1/2 density times velocity at 0.3 squared plus no gravity. And at the end of the fan, the pressures is atmospheric, so that's 0 pressure. And then at point 2, it would be 1/2 density times velocity 2 squared plus gravity plus pressure at point 2. Okay. Now, again, the velocities are the same. You can do it with the mass equation from here, right? So the velocities are the same. So what that means is that this kinetic energy and this kinetic energy are equal. So what is P2? P2 is going to have to be atmospheric, which kind of surprised me, but I guess when you think about it, it has to be, because the kinetic at 2 is the same thing as the kinetic at 3, so the pressures have to be the same as well. Okay, so I guess I was a little surprised by that. But anyway, so pressure 2 is equal to 0. Now that I have pressure 2, I can go back up here to this black equation, this one here, and I can put in the pressure 2. So pressure 2 is equal to 0. So let's pull this guy down. So you have W times 0.5 divided by the Q. The Q was 0.03 equals, and this is going to be 1/2 density times 64 plus 0. Okay, so I'm going to pull out my calculator and calculate the W. Okay, so what I get here is that W is equal to 2.4. Okay, so if you want to look at the units, let's see, the units on density is kilograms per cubic meter. The 64 was velocity squared, so that would be meters squared per second squared. The 0.03 is the volume flow rate, so when you multiply it over here, that would be the volume flow rate comes on the top, so that would be cubic meters per second. And the 0.5 is unitless, so that, let's see, so that would be the cubic meters. It won't, you know, I mean, the units are going to work out perfect. You don't have to worry about them. There, and let's see, cubic meter per second. Okay, so the kilogram, there's 1 kilogram meter per second squared in a Newton. So that means that the kilograms are gone. There's a meter here, kills that guy off, and a second squared. So the unit is a Newton meter per second, and that's a watt. So the units work out fine. So like I was saying, if you use kilogram, meters, seconds, and newtons, then you don't really have to worry about it. Okay, so the work of the pump, or the fan, excuse me, is 2.5 watts. Let me see what else they wanted. They wanted the wattage of the fan, 2.4. The diameter of the fan casing. Okay, so that would be the volume flow rate is equal to area. Well, it's up there. Area times the velocity. So we can calculate the area. So the area is equal to, let's see, Q is 0.03. 0.03 divided by the velocity of 8. So this area should be 0.00375 cubic or square meters. All right, the area is equal to 1/4 pi times the diameter squared, and that equals 0.00375. Okay, so let's see, multiply by 4, divide by pi. Let's see, where's my pi? Divide by pi, and then take the square root of that. All right, so this would be D is equal to 0.069 meters. So that would be 6.9 centimeters. What else did they want? diameter, pressure difference. Okay, the pressure difference is going to be P1 minus P2, or P2 minus P1. Okay, P2 minus P1. P2 is 0. P1 is a negative 40. So that would be 40 pascals. And it rises from 1 to 2. Okay, so that should be it.